over a couple of ideas. Okay, the philosophical underpinning of thermodynamics are issues that we need to, we'll really cover it here. In making measurements that are heat related, energy related, we have to look at a fundamental concept known as system and surroundings. In thermodynamics, it is the foundation of the laws of thermodynamics, and in the ones that we're covering, I include the first law, which is a study of energy changes in physical and chemical process. Delta E changes, E final minus E initial, and is expressed in an equation of two parts, Q plus W, where Q is the heat of reaction and W is the work of the reaction. So we're going to make measurements of how chemical and physical processes take place. We have to have a mechanism by which we can measure things that are going on, energy changes. When we talk about the system, we're talking about an object of interest. And when we talk about surroundings, we're talking about everything else. In chemistry, our objective interest for the most part are chemical reactions. And that includes reactants and products. Now, the issue is how do we measure things that are on this side of the T curve? We are over here. You as an observer are making measurements. And you as an observer have five senses: eyes, ears, nose, throat, taste, smell, and all that stuff. And sometimes you cannot detect what the system is sending you, what signals are they sending to you. And so we have detecting devices. All of this is in the surrounding environment.
Well, the screen, oh, there you go. All right, never mind.
Okay, back to normal. Anyway, the system is acting on the surroundings by sending these signals in various forms. That was electromagnetic energy Alice was looking at through, her eyes. Well, that's just one form. And if you stuck a thermometer in a solution when you poured A and B into it and the temperature went up, you draw a conclusion that that's an exothermic reaction. And if the temperature goes down, the system is drawing energy out of the surroundings. So the reaction's endothermic. So you make interpretations of what the system is doing based on this predetermined format of system and surroundings. And says, in which of the following is work exothermic? When you look at the first law of thermodynamics, you get two parts, Q plus W, and Q is heat of reaction, W is work. When a chemical reaction does work, you look into that reaction in terms of, is it undergoing expansion process or is it undergoing compression process? If it's undergoing expansion, now this only applies to gases. I'm going to put a little note out here, gases only, and say, just to make sure it comes home. If you have an expansion from reactants to products, the molar volumes in the reactants will be less than the molar volume in the products. In other words, there will be more gas volume in the product side. If it is a compression, it'd be the other way around. In other words, the reactants will be greater volume than the molar volume in the products. Okay? Now, in one case, I'm going to talk about, let's do the compression first. If you have a compression, okay, visualize the reaction when it goes down in volume. It's like squeezing a balloon to a smaller volume. Well, when you do without changing any other parameters, the molecules are going to push back on your hand. And in that case, the molecules have to acquire energy, absorb energy. So work is endothermic here in a compression reaction. Over here in an expansion reaction, you think in terms of instantly removing the wall of the balloon and letting the molecules move out into space or farther apart. Well, when that happens, they relax. They're not exerting any forces, or negative forces if you got to be specific. But anyway, work in that case is exothermic. Very important idea and concept here in the entire course of thermodynamics if you get into it. Okay, so looking at the endothermic, I usually use the 3H2 as a gas plus N2 as a gas goes to 2NH3 as a gas. Well, here we have 4 molar volumes going to 2 molar volumes, so it's a decrease in volume, so that's a compression. Therefore, work is endothermic, or change in energy, work energy, let's put it that way. Change in work energy is greater than 0 in the context of how we interpret the compression effect. And if we, in the one in the quiz is water expansion, if we start out as a liquid and go to a gas, right here, the molar volume here in the liquid or solid 0. But here we have 1 mole of water vapor, if you will, and so that is a molar volume equal to 1 unit. So that's an expansion. And therefore work is interpreted as exothermic. That is, work energy is less than 0 right there. So the choice in this collection is the exothermic work because of expansion. Any questions about that? Very, very important in your understanding of how a system is an isolated issue. It can be the discharge tube I showed you a moment ago, sending out signals of electromagnetic radiation, or it could be a reaction delivering energy into the solvent. The solvent's part of the surroundings, as are you and the thermometer and everything of that nature. What's the work in that reaction right there? Is it exothermic, endothermic, or isothermic? Isothermic means zero work on a closed system, no transitions. Is this a expansion or a compression? Or is it none, neither?
Compression.
It's a compression.
Endo.
Okay? So if it's a compression, it's endothermic. And you know that because you're looking at only the gases. Here we have 3 molar volumes, but here you only have 1 molar volume. This is not taken into consideration because it's a liquid. Liquids do not demonstrate volume in the context of a gas. That's what we're trying. Does that help, Henry? That help? Let's see here, okay? Where I write in the water at the end of it as vapor, as steam or something, because the combustion of the methane first produces a steam, okay? And in this case, you have the same number of molar volumes on both sides that's equal, and so that's an isothermic process. Isothermic work processes. That is, work is equal to 0. There's no change in volume, which specifies the closed system, like that. Number 2, now this is the essence of what I was trying to share with you. When measuring energy changes, when any kind of measurement, it doesn't matter, the electromagnetic radiation, okay, is sent to you and you're measuring it or detecting it in your eyes and say, okay, that's lavender or purple or, and what else was going on in there? Anybody notice a weird sound? You know, that kind of stuff. So all of those are signals. And you choose the signal that you want to measure, okay? You, detectors, your 5 senses, and everything else is the surroundings. And the object that you're measuring or studying is the system. And this is where you detect / measure signals from object of interest. Good point? Okay, so in this case, all the measurements are being done in the surroundings and measurements and interpreted in terms of the system, like that. Hope that helps. Okay, number 3, a reaction is conducted in a solution phase. Let's say we have an acid solution, and we have a base solution, and then another beaker, and here's our reaction, and so we pour these in here, like that, and we've got, say, a thermometer in here. And what you observe is an increase in temperature. Oh no, this one particular one, we have a decrease. That's the way I specified it. It decreased. So energy is being taken out of the thermometer into the reaction. So the reaction's absorbing energy. And when we talk about endothermic and exothermic terms, it's always defined in terms of the reaction or the system. So as the thermometer goes down, you interpret what the reaction is doing. Well, that's the system. And so if you notice a decrease in temperature, it means this reaction is gaining energy. And if it gains energy, that is an endothermic process. Okay? The reaction's gaining energy, but it's exothermic to the surroundings. But we do not define exo and endo in terms of surroundings. They're always in terms of the system. H1. Okay, so we look at this reaction as I've written it out, and the question is the net energy change is what? Okay, the net energy change associated with this reaction would be blank, and the work would be blank. So I split it into two parts here. Okay, when we talk about the entire first law application, when you apply the first law to chemical reactions, what are you calculating? What does it mean in terms of the outcome of the numbers or whatever you get? This is a change in internal energy. Now, there are three kinds of energy in physics: kinetic, potential, then this, internal energy. Internal energy, as you recall from last lecture, hopefully, that is energy due to its structure, chemical structure, and state of existence. So when we look at the reactants over here, their structure and state of existence are different than, this may be still a gas over here, state of existence, but ammonia certainly doesn't have the same chemical structure. So as those chemical structures change, so does the internal energy content of the system, which is the reaction itself, and here. Now, if we isolate the issues in here, well, let's put it this way. The internal energy, delta E net, is Q plus W, which can be written as delta H of reaction, and this is the, see it right here, it's delta H of reaction plus 2.5 absolute delta V. And then you assign a plus or minus based on expansion here, and then you add them together. In this particular case, the minus 91.8 kilojoules is your delta H right there. But it is a compression by 2 molar volumes. So we want to add 2 molar volumes in here. That's 2.5 times 2. But as a compression, it is endothermic, and so we have to put a sign plus on that right there. And then we have the delta E net, which is minus 91.8 plus 5.0, all in kilojoules, and that will be the net. Okay, so the net energy change is 86. It's still exothermic relative to the big picture of the reaction. Typically the work function is very small, and you'll find many tables and publications that won't even take the work into account, regardless of expansion or compression. But I'm obligated to share that with you, certainly. The net energy change is still going to be exothermic, and the work, we've already said, is endothermic. And so D choice in this issue is appropriate. Okay. And this one, there's a couple of issues I want to touch on, and the idea that you're looking at here. One, I want you to review Hess's law. You recall Hess's law, and I put a video on online. So if you want to go in there and look at an older video, it kind of goes through some problems on this. But Hess's law equation is the heat of reaction under standard conditions. That's 25 degrees in 1 atmosphere right here, is the sum of the moles of the standard heats of formation of your products minus the sum of moles of standard heat of formation of the reactants. So here we have the products and reactants. So we added them all up. We only have one component each side of the arrow. So the heat of reaction is products minus 241 kilojoules minus a minus 285 kilojoules, and so that becomes 285 minus 241 minus plus kilojoules, and the delta H only in the first law is 44 endothermic kilojoules, like that. So that's only one calculation. This is part one of the first law. First law is delta E equals delta H plus actually P delta V, which I have given you in 2.5 delta V. This is the part we just calculated here. You're through. That's part one. Part two is the work. The reaction, and in this case is P delta V, which I'm translated as 2.5 delta V molar volumes, and this comes out as 2.5 times 1, and that comes out in kilojoules, and that's 2.5 kilojoules of work. But you have to look at it and see whether or not you're compressing or expanding. Well, it's an expansion this time because you're getting from 0 molar volumes, liquid to gas, and so we have to apply a negative sign into the work function. I think I showed you this last time. I'll show you again in a minute. So these are the two parts. This is Q and this is W in the net energy calculation, Q plus W, which is 44 kilojoules endothermic plus a minus 2.5 kilojoules, and the 41.5, yeah. That energy change, and from this form of the first law, this problem is B choice in here. Now, I showed you this, I think, last time. First law equation can be written in either form. If the one that I just worked through with you is this one. Now, the difference in these two is you must interpret your work function in terms of exo and endothermic. And so if it's endothermic, you apply a plus W, or if it's exothermic, you assign a negative to it. Over here, if you see this form that's published, and both of them show up, believe me, you don't have to make a determination here. You just calculate your delta V, and it'll take up the, it'll automatically give you the results of what work is. Delta V proportional to the work energy. Okay, an example is the change in to gas plus N to gas real quickly, so you'll have this available if you never need it. NH3 gas. I'll show you delta H of the reaction minus 91.8 kilojoules. So if I'm going to calculate the delta E net using Q plus W, then it would be minus 91.8 kilojoules plus 2 molar volume change times 2.5, and this is a compression reaction. Okay, so I have to put in here a plus to identify that. 2.5 times 2 kilojoules, and that comes out, get back down here. That's 86.8 or something like that. Exothermic. Okay, if I did it over here using this minus right here, delta E net is equal to Q minus W. You keep in mind Q is the delta H here, minus 91.8 kilojoules, minus, all you have to do is put 2.5 delta V. You don't have to worry about pluses and minus. The change in here is what? 5 kilojoules. Right there, and it's minus 91.8. It's a decrease, excuse me, I'm sorry, 2.5 times decrease minus 2 molar volumes. That's where you get your negative put into kilojoules. Right there. That's what, and so that's a 2 negative, positive, 2 times 2.5 is 5.0. It all comes out in kilojoules, and this comes out 86.8 kilojoules also. So both of them give you the same answer, but in one case you have to make an interpretation of expansion, compression work. This one you don't. Okay. Let's see. Any questions? So we're going to add to this real quickly.